Writing code in a black and white terminal window restricts you to a text-based, keyboard-driven environment. But the software we interact with daily exists as graphical interfaces inside web browsers and on mobile phones. Moving from a local command line script to a web application requires a different system of organization. The underlying programming logic, the variables and the loops, remains identical, but the deployment mechanism shifts from a single local machine to a global network. This architecture relies on two distinct layers. The first is the physical infrastructure, a network of protocols and routers responsible for transmitting packets of data across thousands of miles of wire and wireless connections in milliseconds. The second is the presentation layer, built on a three-part system. It uses HTML to define the structure of the data, CSS to dictate the visual style, and JavaScript to execute logic on the user's device. Understanding the interaction between these network protocols and this layered presentation stack allows developers to move beyond writing local scripts and begin building global applications. The Internet is an interconnected network of networks. When you transmit data across it, that information is packaged into digital envelopes called packets. Hardware routers read the destinations on these packets and direct them along geographic paths to reach the target machine. To ensure those packets arrive at the correct destination, every device needs a unique identifier. Under the Internet Protocol standard known as IPv4, this identifier is a 32-bit address. Because 32 bits allows for roughly 4 billion unique combinations, the protocol mathematically caps the total number of connected devices at that limit. Because we have exhausted those 4 billion addresses, the industry is gradually transitioning to IPv6. This standard uses 128-bit addresses to supply more than enough unique identifiers for the foreseeable future. Getting the packet to the right machine is only the first step. A single server handles multiple services simultaneously, serving web pages, routing user emails, and managing video conferences. The Transmission Control Protocol, or TCP, adds specific port numbers to the packet. Port 80, for instance, tells the receiving server the packet is a web page request rather than an email. TCP performs a second function. Sending a massive file over the network in a single block would tie up the connection and prevent other users from accessing the server. TCP fragments the large file into many smaller packets, assigning each a sequence number so the recipient machine can reassemble the complete file upon arrival. Humans do not memorize 32-bit IP addresses. When you type a domain name into a browser, a domain name system, or DNS, server acts as a directory, translating that text into the machine-readable IP address required to route the packet. Similarly, when you connect your phone to a new Wi-Fi network, a dynamic host configuration protocol, or DHCP, server responds to your device by automatically assigning it a temporary IP address. TCP, IP, DNS, and DHCP function as the logistical infrastructure of the web. They operate in the background, guaranteeing that data can travel between any two endpoints before any code from an application is processed. Once the network connection is established, the client and the server use the Hypertext Transfer Protocol, or HTTP, to exchange files. This protocol relies on text-based verbs, like GET, which the browser places inside its initial data packet to request a specific web page. The server processes that request and responds with an HTTP status code. If the requested file exists and the connection is functioning, the server replies with the code 200, indicating that the operation was successful. If the web page has been relocated, the server returns a 301 status code, meaning moved permanently. This acts as a network-level detour sign, supplying a new URL and forcing the browser to automatically reroute its request to the updated location. If a user requests a file that does not exist, the server generates a 404 status code for not found. HTTP provides the conversational framework governing these interactions. It allows an isolated client device to negotiate with any server on Earth, establishing the parameters required to download the assets of a web page. The primary asset returned by the server is an HTML file. HTML is a markup language. It uses tags and attributes to define the structure of data, though it lacks the variables and logic of a programming language like C or Python. When the browser reads this document, it dynamically parses the tags to construct a document object model, or DOM. This creates a functional tree structure in the computer's memory. Every modern web page builds off the same skeletal framework in this tree. A doc-type declaration sits at the root, followed by the primary HTML node. That node branches into a head tag, storing metadata, and a body tag, holding the visible elements rendered in the viewport. Browsers ignore raw white space in the document. To format text, developers must use structural tags. Wrapping text in paragraph tags creates discrete blocks, while H1 through H6 tags establish a hierarchy of headings. Complex data structures require nesting tags. A list tag acts as a container, requiring list item tags nested inside it to denote each separate point. While most HTML elements require an opening and a closing tag to dictate where the content ends, image tags are empty elements. They simply point to a file source and embed the graphic directly into the layout without needing a concluding tag. HTML defines the structural blueprint of the web. It provides the nouns of the application, the text, the links, and the media, creating a framework that remains visually unstyled without further instruction. To control visual presentation, the stack introduces cascading style sheets, or CSS. This language modifies the visual properties of HTML elements using key-value pairs to dictate exact parameters for color, font size, and layout. In CSS, styles applied to a parent node in the DOM tree cascade downward. This property ensures that aesthetic rules pass automatically to all nested child nodes within that branch. Writing these styles directly onto individual HTML elements is inefficient. To execute styling at scale, developers write CSS in an external file and use selectors to target specific nodes within the DOM. An element selector targets every instance of a specific HTML tag. A single rule for the body tag can dictate layout instructions across the entire web page. When styling needs to be more precise, developers use a class selector. This binds visual properties to any HTML tag carrying that specific class attribute, allowing them to style modular groups of content independently. For a singular component on the page, an ID selector applies visual rules to one specific, identifiable element within the tree. CSS separates visual design rules from the HTML file. This allows developers to reskin an application's aesthetics without altering its underlying structural memory tree. HTML and CSS are static. Interactivity relies on JavaScript, a programming language equipped with variables, conditionals, and loops that executes locally within the client's browser. JavaScript's primary utility is its ability to listen for user events, like a mouse click or a keystroke, and mutate the DOM tree in real time, bypassing the need to request a page refresh from the server. Developers typically wrap their JavaScript logic in an event listener, waiting for the DOMContentLoaded signal. This ensures the browser has fully constructed the structural tree in memory before the code attempts to alter it. Once the tree exists, the addEventListener mechanism binds a block of executable code to an exact HTML element. It remains dormant until the designated user interaction triggers it. These triggers dynamically rewrite a page's styling. A click event can execute a function that intercepts CSS properties and instantly alters an element's background color. JavaScript also allows for continuous background execution. The setInterval function creates a repeating loop that swaps an HTML element's visibility status every few milliseconds, creating a blinking effect. This real-time mutation powers features like search autocomplete. As the user types, JavaScript reads the input, cross-references it against local data, and injects matching results as new list nodes directly into the structure. JavaScript also bridges the gap between the browser and the device's hardware, allowing scripts to query GPS sensors to pull precise geolocation coordinates. JavaScript provides the active verbs of the web stack. It takes the structural HTML framework and the painted CSS layers and animates them, transforming a read-only document into a responsive application. Every interaction on the web follows this cycle. It begins when a user enters a URL, prompting the client machine to format an HTTP GET request and fire a data packet into the network. That packet navigates global router pathways via TCP/IP protocols until it reaches the target server and secures a return package. The local browser reassembles the return packets and parses the HTML text to construct the foundational document object model tree. CSS rules then sweep across that scaffold in a cascade, mapping precise color, layout, and typographic parameters onto the structural nodes. Finally, the JavaScript engine activates, binding event listeners to the layout and waiting to mutate the memory tree the moment the user interacts with it. By combining reliable network routing with these three interpretation languages, developers possess the foundational tools to build and deploy applications on the modern web.